In recent years, the pursuit of life beyond Earth has taken an incredible leap forward thanks to the groundbreaking capabilities of the James Webb Space Telescope, JWST. The NASA-led telescope, launched in late 2021 with the collaboration of ESA, European Space Agency, and the Canadian Space Agency, CSA, has redefined how we study the cosmos. From its orbital position nearly 1 million miles from Earth, the JWST has unveiled worlds that are astonishingly similar to our own, yet unique in ways that could make them even better suited for life. These so-called super-Earths are planets that are larger than Earth but smaller than gas giants, often rich in water and located in what scientists call the habitable zone. But how do we know these planets exist, and what makes scientists so optimistic that life could be found there? The answer lies in the cutting-edge technology aboard the JWST, which allows it to probe the atmospheres, climates, and potential biomarkers on distant planets with an unprecedented level of accuracy. One of the most significant methods JWST uses to study these exoplanets is spectrometry. By analyzing light that passes through or reflects off a planet's atmosphere, scientists can determine its composition, including the presence of elements like water vapor, methane, and oxygen, key indicators of habitability and potential life. This method is so sensitive that JWST can detect even small quantities of these gases on planets that orbit hundreds of light-years away. For instance, K2-18b, an exoplanet discovered roughly 124 light-years away in the constellation Leo, has been hailed as a second Earth because JWST's spectrometers detected signs of water vapor in its atmosphere. This discovery was exciting because K2-18b orbits its star at a distance where temperatures are just right for liquid water to exist on the surface, a critical factor for supporting life as we know it. Known as the Goldilocks zone or habitable zone, this sweet spot is a key criterion when scientists evaluate the potential habitability of any exoplanet. K2-18b is not alone. The JWST has identified other promising candidates that have conditions favorable for life, which are collectively known as super-Earths. Unlike gas giants such as Jupiter or Saturn, super-Earths are rocky planets with a size and mass between that of Earth and Neptune. Many of these planets have an abundant water supply, possibly in the form of vast oceans or thick atmospheres filled with water vapor. This trait makes them particularly interesting to scientists because water is one of the essential building blocks of life. With the discovery of these super-Earths, the hope of finding extraterrestrial life has taken on new dimensions, leading scientists to speculate that some of these worlds might even be better suited for life than Earth. One of the most fascinating aspects of JWST's capabilities is its ability to detect artificial light, a potential indication of intelligent life. While natural light sources are abundant in the universe, the presence of artificial light, particularly if it displays unique wavelengths or patterns that differ from natural sources, could suggest advanced civilizations on other planets. The JWST's highly sensitive mid-infrared instrument, MIRI, can distinguish between artificial light and natural light, allowing scientists to search for signs of technology in distant worlds. Though it has not detected any artificial light so far, this capability remains a fascinating possibility, one that brings us closer than ever to discovering signs of technological life beyond Earth. Such advancements hint that we may not be limited to searching for simple microorganisms. Instead, we may one day discover evidence of other technologically advanced civilizations. The JWST is an unprecedented feat of engineering, built to detect the faintest light from the most distant galaxies and planets. This feat has been made possible through its intricate honeycomb-shaped mirrors, each coated in a thin layer of gold to enhance its ability to capture infrared light. Traditional telescopes struggle with detecting exoplanets directly because these planets are minuscule in size and do not emit their own light. However, the JWST bypasses these limitations by employing two main techniques: gravitational microlensing and transit observations. In microlensing, the telescope detects a planet's gravitational pull as it passes in front of a star, causing slight variations in light that can reveal information about the planet's mass and orbit. Meanwhile, transit observations allow JWST to detect the subtle dimming that occurs when an exoplanet passes directly between its star and the telescope. By measuring this dimming, scientists can infer the planet's size and orbital period, which provides clues about its potential habitability. The search for habitable exoplanets has been ongoing since the mid-1990s, when astronomers first detected planets outside our solar system. But the JWST has revolutionized this field, bringing unparalleled precision and depth to our observations. Prior to JWST, most exoplanet discoveries were made with the Hubble Space Telescope and ground-based observatories, which provided only basic data. However, the JWST's advanced infrared capabilities allow it to penetrate clouds of gas and dust, capturing details that were previously invisible. This is particularly useful for studying exoplanets in systems with red dwarf stars, which emit less light than our Sun but are abundant throughout the galaxy. Exoplanets orbiting red dwarfs are more challenging to study, yet many of these planets are located within the habitable zones of their stars, making them prime candidates for further exploration. In addition to K2-18b, another compelling target is Ross 128b, an exoplanet only 11 light-years away. Unlike many exoplanets orbiting red dwarfs, Ross 128b orbits a relatively calm star, which means it is less likely to be bombarded with harmful radiation. This stability significantly increases the likelihood that Ross 128b could harbor life, or at least an environment suitable for it. Furthermore, scientists hope to use JWST's spectrometers to confirm the presence of water vapor or other biomarkers in Ross 128b's atmosphere. Should these biomarkers be detected, Ross 128b would join the growing list of Earth-like planets that merit close observation in the coming years. Meanwhile, the discovery of Proxima Centauri b, an exoplanet in our nearest neighboring star system, has sparked intense interest from scientists and space enthusiasts alike. Orbiting the red dwarf Proxima Centauri b was initially hailed as a potential second Earth due to its size and location within the habitable zone. However, further observations revealed that Proxima Centauri often emits powerful stellar flares, potentially subjecting Proxima Centauri b to harmful radiation. This revelation has dampened hopes of finding life there, yet the discovery remains significant because it highlights the importance of studying each exoplanet in detail. Even if Proxima Centauri b itself proves inhospitable, scientists believe that other planets in the Proxima Centauri system could still hold potential for habitability. As the JWST continues its mission, it is set to analyze an extensive catalog of exoplanets, some of which could very well be our best chances at finding life. Currently, we know of over 5,000 exoplanets, only a fraction of which are rocky and Earth-like. The search for habitable worlds focuses primarily on these rocky planets because they are more likely to have solid surfaces and liquid water. Yet, these worlds are also some of the hardest to detect due to their small size and lack of light emissions. The JWST's precise instruments, however, have already proven that these obstacles can be overcome. Equipped with some of the most advanced technology ever created, JWST can capture faint traces of light and analyze the atmospheres of these planets with unprecedented accuracy. But JWST's journey is not limited to finding life. The telescope has also set its sights on binary star systems, where planets orbit not one but two or more stars. These Tatooine planets, named after the fictional Star Wars planet with two suns, are far more common than scientists once believed. Binary star systems can be incredibly dynamic, with complex orbits and extreme temperature variations. While life as we know it may be difficult to sustain on such worlds due to intense radiation, the discovery of such planets expands our understanding of planetary systems and suggests that life could exist in forms or locations we have yet to imagine. Another ambitious project related to exoplanet exploration is the Starshot Breakthrough Initiative. This privately funded endeavor aims to send miniature probes to Proxima Centauri, the closest star system to Earth. If successful, the project could provide the first-ever images and data from an exoplanetary system outside our own. These tiny probes, equipped with cameras and sensors, are designed to travel at nearly the speed of light, allowing them to reach Proxima Centauri within a few decades. Although the project faces technical challenges, it represents humanity's desire to reach out and explore distant worlds, a goal that the JWST's discoveries have only further inspired. The potential discovery of super-Earths like K2-18b brings humanity closer than ever to finding life beyond our solar system. A super-Earth, by definition, is a rocky planet larger than Earth but significantly smaller than gas giants like Neptune. What makes super-Earths so fascinating is not just their size, but the fact that they often possess thick atmospheres that may be conducive to sustaining life. K2-18b, for example, has an atmosphere that appears rich in water vapor, a critical component for biological processes as we understand them. The planet's atmosphere, detected with astonishing precision by JWST, suggests that it may host vast oceans beneath dense, potentially habitable clouds. Thanks for exploring the cosmos with us at Space Lab. Don't forget to subscribe for more thrilling discoveries that await us in the universe.